Прошу поприветствовать Илья Сускевер, собственной персоной из Малта.
Okay, so it's very nice to be here remotely. Thank you very much for the invitation. So my name is Ilya Sutskever and I work at the Google Brain team. And in this lecture, I'll give you a basic overview on deep learning, on how it works, roughly speaking, why it works, what is it good for, and some of the recent developments, which are quite interesting. And by the way, most of the work that I'll describe has not been done by me. It's mostly been done by my colleagues in the Google Brain team. So before I continue, I'd like to get a sense of how many people. Okay, let me ask you a question. I want to see a show of hands. How many people know the backpropagation algorithm, so that I could calibrate my presentation towards the right audience? Okay, so it looks like a fraction, but not a huge fraction, I think. Okay, so what is deep learning? Deep learning is nothing but a modern reincarnation of artificial neural networks from the 80s and the 90s. And basically, an artificial neural network is this large system which has many layers of neurons, and there is a mathematical function that tells you how to compute each neuron. And this function is very simple. And then you can you can give this neural network an input, and it will produce an output. And so it's loosely inspired by the brain, and the higher levels, the higher layers of the neural network are able to compute more abstract representations. So let's delve into it into a little bit more detail, because this point, I think, really explains why deep neural networks are as successful as they are. So we will consider the problem of supervised learning. In supervised learning, you want to learn a function from one space onto another space. For example, you might want to learn to map speech to text, or you might want to learn to map, let's say, you might want to learn to map images to their categories. So you have these functions which you want to learn from input-output examples. And so the fundamental element of the neural network is the neuron, which is shown in this figure. So the neuron is a very simple function. It's a function that maps the x's into an output with a very simple formula. And the thing to know is that the function is determined by the weights, so that if you change the weights, you change the function. And so the output of the function is a scalar. So if you know the weights, then for any set of inputs, you can compute the output. So the neuron is a truly simple computing element. It is very, very trivial. Now, a neural network is the object that you get when you arrange these neurons into layers. So once you take the neurons from here and you arrange them into layers. And now, once you know the input, you can compute the values of the neurons in each layer until you get to the output. So this is what a neural network is. It's simply an arrangement of neurons. Now, neural networks are interesting because there is a simple algorithm for finding the we can define a neural network, but we also want to learn it. And the way learning works is that you need to have a lot of input-output examples. You need to have a lot of input-output examples of the desired behavior, which then you learn to emulate. And the way the learning algorithm works, which by the way is called stochastic gradient descent, it is the only algorithm that everybody uses, and it turned out to be more successful than all other algorithms combined. You just pick a random training case, or a small collection of training cases, and you run your neural network on the input X, and then you modify the connections of your neural network so that its predictions will be slightly closer to Y. And by repeating this process many times, eventually the connections converge to a configuration that is able to produce the correct output on most of the training cases. And what's really nice is that I won't describe how we modify these connections, but there is a simple algorithm which you don't even need to implement because it's done by the excellent software packages that exist for neural networks. Okay, well, I have a slide on that. The way the modification works is that, yeah, you take the derivative, and the derivative of the error with respect to the weights tells us how we should change the weights in order to improve the model slightly. And so, but in some sense, the back propagation and the gradient descent were used to training machine learning models for a long time. They used to train linear regression. What is more interesting, in my opinion, is to try and understand why is it that deep neural networks can solve speech recognition and they can solve vision. Why is it that they do better than other models? I think it's a legitimate question because it's not, and it's also not an obvious question. So, from the practical perspective, to understand why neural networks are successful, we need to accept two facts. The first fact that we need to accept is that a 10-layer neural network can be trained. So at this point, I would say it's even more than 10, but definitely 10 layers. If you have a neural network with 10 layers, then you need to initialize it in a certain way, but then backpropagation will succeed on most realistic problems. And so this is a very important fact because it means that if you have a 10-layer neural network, you can find a good configuration of weights. But the second thing about neural networks, which is just as important, is that a good configuration of weights exists. In other words, that for some setting of the weights, you will have a high-performing function. And this is really important. If your machine learning model is such that for all configuration of weights you will not get good performance, then it's very clear that good performance will never be achieved, no matter how good your learning algorithm is. And so it is important to get some understanding of the class of functions that neural networks can compute. So let me tell you some results which I think are a bit counterintuitive as to what neural networks can compute. So if you have a neural network with 2 hidden layers of modest size, then this neural network can, for example, sort n bit numbers in 2 hidden layers. I think you should find, at least I found it counterintuitive when I heard about it, because I always thought of sorting as of something which requires a logarithmic number of steps, logarithmic in n. And here it turns out that in a neural network, with layers that aren't very huge, can sort n bit numbers with 2 hidden layers. You can also multiply n bit numbers with a neural network with 2 hidden layers which are not very large. And so this should be a strong indication that neural networks can truly compute a lot of very, very complex functions, the kind of functions we may perhaps care about in our applications. And so the sorting result suggests that neural networks are more economical than Boolean logic, because it is not hard to convince yourself that a Boolean circuit with 2 not exponentially large layers cannot sort n bit numbers, but neural networks can. So therefore, the threshold neurons are more economical than logical neurons. So, but the more convincing, in my opinion, more convincing argument as to why neural networks should succeed is simply the argument that comes from the processing speed of humans. So we know that human perception is very fast. We can see extremely quickly and we can hear extremely quickly. We can recognize emotions and we can understand some amount of language really quickly. Some people can do really rapid speed reading. And experts can solve lots of problems. They can see the solution very quickly and many more. So humans can solve many problems really quickly in a fraction of a second. But it is also known that our neurons fire at most 100 times a second and possibly less. So this suggests that if you have a large neural network with something like 10 layers, maybe a little more, then it should be able to achieve really high performance on vision and speech with very high probability. So this argument, is not it's not a proof because it could turn, because this argument says that makes the strong assumption that the artificial neuron is somehow comparable to the biological neuron. And it is not something which was known, because it is, for example, some people believe that the biological neurons are much more complicated and much more powerful than artificial neurons. But on the flip side, some other people believe that biological neurons have a lot of noise in them, and you would need thousands of biological neurons to replicate one artificial neuron. But in any event, this hypothesis, if you take it seriously, suggests that perhaps with as little as 10 layers, you should be able to do pretty good perception at the very least. You should be able to do well on tasks on which humans do well also. And so this is the the scientific way of verifying that. If you have, you can ask people to, let's say, click on a button as soon as they see an object of some kind, and so that really can give you an upper bound of total time that humans need to process. So we can perhaps take this idea slightly, and you can call this, make a strong claim, which I call the deep learning hypothesis, that anything humans can do in 0.1 seconds, a large, deep neural network with 10, maybe 20 layers can do as well. And this is very powerful. This, in my opinion, is the reason why deep neural networks are successful. I mean, it's hard to argue that, we cannot argue that deep neural networks are successful from first principles. Instead, we argue that because humans are successful, and since humans have neurons and artificial neural networks have neurons too, and if these neurons have anything in common, they should succeed as well. But empirically, after the fact, we can look back and say that this hypothesis is quite true. Deep neural networks do really well on perception tasks. And that also suggests that artificial neurons are not a bad model for real neurons. So let's discuss some concrete examples. What kind of functions can we actually learn in practice? What have been done? And so, for example, at this point, many of you know that you can take an image as an input and produce the category as an output. You can take the speech as an input and you can produce the text as an output. You can take you can take a query in a document and you can predict the probability of a click. You can try to do these things. Translation. You can even map images to text. You can even do that. So this is cool. And I can now mention a little bit of some of the extremely excellent deep learning work that's done at Google. So at this point, Google is really into deep learning. There are we use lots of CPUs and GPUs, and we publish a lot of papers. And at this point, we had 47 production launches of deep neural networks in Google, which is fairly significant. And I think there will be a lot more in the future. So it's very nice. And we've had a lot of publications on lots of different domains. So for example, distributed training, recognition, image recognition, and video activity recognition, and OCR, and machine translation, and language understanding, and advertising. We had publications on all these. So Google is really active. I'm perhaps advertising Google a little bit. And so now we can discuss some of the applications in a bit more detail. So the first really serious application of deep neural networks was for speech recognition. And it was in fact pioneered by my former colleagues from Toronto, George Dahl and Abdul Rahman Muhammad. And later on, this work has been extended and improved at Google, and they've been able to train a really good speech recognition system that resulted in the first neural network. Once the neural network was added to the Google speech recognition system, they had a huge, massive improvement, and it was launched 3 years ago, so quite a long time ago. And in that original system, the neural network would only classify small portions of the speech signal. So it would classify each small chunk of the speech signal into an acoustic category, which would later be processed by complicated HMM transducer, which is a little hard to understand. Later this part has been replaced with an LSTM, to those of you who know what it is. Vision. So, and by the way, so the improvement, and the LSTM is, if you use voice search on your phone, the LSTM is you may have noticed that things have improved fairly recently, or maybe in the past 6 months, and the LSTM is the reason why. So another really big application is the image, is neural networks for images. And so the same convolutional neural networks that were pursued by Lacan many years ago. So later they were drastically improved by myself and Alex Krzyzewski and Jeff Hinton, where we got the first really strong results on vision. And later these results have been drastically improved still. So they improved our old results from 16% down to, at this point, this slide is not even accurate. It's now down to 4.8%. So this is the inception neural network, which is a little hard to understand, what's going on there. It's a complicated architecture, but 4.8% of 5 is just unbelievable, in my opinion. And you can also test this if you use Google Photos on your phone. You can, whenever you search for anything, it's being used there, among other places, and it actually works. If you've been in the field for maybe for some numbers of years, you may remember that vision didn't work at all, and now it basically just works, and the progress is just incredible. And so yeah, this improvement. So these are the ImageNet results. So this is 25. This is the top 5 error before ConvNets, 25.7, and then we introduced the ConvNet 16.4, and then it's like shrunk, exponential reduction in 3 years. And the data set is basically solved. And you can see some examples. I mean, I'm sure many of you have seen those examples already, but I find it, even now, I find it amazing to look at how it recognizes these flowers. How does it know? It looks at these flowers and recognizes them. And it recognizes the food, and it makes mistakes sometimes. But this is not, so by the way, these are not predictions. These predictions are not made by an inception model. So I suppose it is quite possible that the inception model would not make these mistakes. But the point is, it does very, very reasonable things. Here it found Yoda. It identified this little toy as Yoda, which is quite nice. And so then there was other work as well, where, for example, the convolutional neural networks were applied to house number recognition, and they were very accurate as well. I mean, at this point, it's pretty expected. And they were applied to text recognition of text and images, and this was work done by Matt Saylor, who was an intern at Google at the time. And basically for anything, for vision, if you have a vision task, you've got a big data set, and you can get such high performance now. And of course, there are good open source tools which can let you try out these models. So one application that's particularly important, I suppose not application, but one category of application that's important is the category of applications whenever you have sparse input data. So that's important because if you're working in a company, then usually you have lots of features, lots of kind of, you tend to have extremely high dimensional descriptors, of which only a small number is non-zero. And so neural networks very likely handle this case as well. And so in particular, I would like to mention some work on word embeddings, namely Word2Vec, and this was work by Tomasz Mikolov, who has since left Google. And the idea is, when it comes to, but before we go into Word2Vec, we will discuss the more traditional embeddings, where you just basically say you have your input, and you just do a sparse matrix vector product, and then you feed it to your neural network, and you make your prediction. And you can do supervised learning on this prediction, and it works really well. This works reliably, consistently well, and it's super robust, and that's probably the thing most people will be doing. This is probably going to be one of the most commercially used neural network architecture. But the Word2Vec model, the skipgram model, is is quite a different approach because it is unsupervised. It is a very rare thing to have unsupervised model, unsupervised learning. And in this case, the model tries you're having a very, very compact model that tries to predict the neighbors of a word. So the way it works is that you say you got words, and you want to find vectors for these words. And you want to make sure that words that occur frequently, they have similar vectors, and words that they have a large and positive inner product, and words that never occur together should have a large and negative inner product. That's what it boils down to. So it's a very simple unsupervised objective that's formulated in terms of inner products of the vectors of words as they co-occur together. And when you do that, you get very, very nice word vectors. They have extremely nice neighborhoods. For example, you look at car, the neighborhoods of car are going to be cars, sports cars, and tiger shark is going to be bull shark, and all kinds of sharks. So these vectors find really great neighborhoods, and they're very fast to train as well. But what's much more surprising, the thing that surprised the community, is that you could do this word analogy. And the word analogies, they work, and they work pretty accurately, and this is a cool result. And at this point, we have a reasonable understanding of why it happens, but it's still slightly complicated, so it's not easy to explain. But there are already papers that explain why this is, and it has to do with simple properties of the co-occurrence of words. So in particular, here is a visualization of the word analogies result, where you take a set of countries and a set of capital cities, and you project them down to a two-dimensional PCA, to the two largest principal components. And you see that these cities and countries are laid on parallel. So you can see that explains why the word analogy should work. And the same, another demonstration of the word analogy for a different set of words here is fallen, fall, fell, drawn, draw, drew. You can clearly see that the relationship between those triplets are the same. So it's a really nice result where you show how the geometry of meaning is preserved across different sets of words, which is really cool. And so, but now we can discuss a slightly different neural network, which is also quite cool, and this is something that I was involved in as well, together with my colleagues Oreo, Vinyals, and Kwok Lee. And basically what we were really interested in doing is we wanted to do machine translation directly, end to end. We wanted to build a system that would take a sentence as an input and produce a sentence as an output. And we wanted to use a sequence model, so we used a deep LSTM. So an LSTM is this model which is, it's an important model. So let me make a little bit of a question. How many people know what the LSTM is? Please raise your hand. Okay, so some fraction. I should still explain. So how many people, by show of hands, how many people know what a recurrent neural network is? Okay, so the number that I see from my vantage point is not huge. So basically, a recurrent neural network is a neural network that can process sequences. So you give it different inputs at different time steps, but it uses the same weights to process those inputs. So you have this very, very natural sequence model. You can think of the layers as of the neural network state in time. Now, the problem with recurrent neural networks is that they turned out to be difficult to train for a variety of technical reasons. And then there is this other model, which is called the LSTM, the long short-term memory. It was invented by Hochreiter and Schmidt-Huber. The LSTM is easy to train. Now, unfortunately, I don't have slides that explain why the LSTM work. But if you're curious, you should look it online. It's not complicated at all, and it's easy to implement. It's easy to implement and it's easy to use, which makes it so significant. But the point is, the LSTM, so you have this model that can process sequences. And so the way we set the model up is we basically have this, so we use an LSTM so this figure illustrates the model, but it does it in a way that's perhaps not so easy to understand. Let's see if we have a slide. Basically, imagine that this circle, each circle here, is a big vector, which is a state of the LSTM. And so on the blue side, you have the input sentence. And the big LS and the very large LSTM reads each word on the input sentence one at a time. Then it produces a large vector which represents the input sentence. And then it produces the output sentence one word at a time as well. So this we used an LSTM in this manner. And we were able to get state-of-the-art result on a public WMT translation dataset. To get state-of-the-art result, we also needed the help of Thang Long, whom I forgot to mention in the slide. He improved our model even further. But basically, you have this really simple model. The model simply says you have a sequence. It looks like this. So this is the model. You got this deep LSTM. So each little circle corresponds to a stack of these layers, and you simply say read the input sentence and produce the output sentence. And the very surprising thing, at least to me, was that this approach was successful. That a neural network an LSTM was able to learn to map a variable-sized sentence onto a fixed-sized vector, and then to decode this vector into a translation. So another very cute application that was done by Oriol Vinyals and Kwok Lee, this was done without me, is to just apply this LSTM to make a very, very simple chatbot on tech support chats. And you have this. It was possible to get. There is a paper called the Neural Conversation Model, and the conversations that it had were kind of amusing, and if you didn't pay attention, it looks like it might even understand something a little bit, although of course its understanding is very small. So in this case, the LSTM simply would predict what would the tech support say given the sentence that the customer says. So it was a very direct sentence to sentence to sentence approach. And so this is another. So this is how the model works. Again, it's the same thing but in a different figure. You got your input sentence, which is processed by an LSTM. You get a vector, and then you have an output, and then you produce the output one word at a time with an LSTM as well. And you can do a small visualization. So one of the nice things about this model is that it maps sentences to vectors. You can take a sentence, which is a variable size object, and you can map it into a vector. And that's a really good property to have. Mapping sentences to vectors is, it's useful because then you are able to apply geometric ideas to sentences as well. And so here, what we showed, we took a small set of sentences, we computed their sentence representation, and we projected them down to PCA. And here you get the desired behavior. Mary admires John, Mary is in love with John, Mary respects John, John admires Mary, John is in love with Mary, John respects Mary. So it shows that the sentence is correct. And another example here, I was given a card by her in the garden she gave me a card, she gave me a card in the garden. She was given a card by me in the garden I gave her a card, I gave her a card in the garden. So all these sentences have one meaning, and these sentences have a different meaning, even though these sentences say it in different words. So that's quite nice. I should also say that the translation model ended up producing sentence representations which were not very good. And a paper which is called Skip Thought Vectors, which is done by Ryan Kyrus and his colleagues from Toronto, they were able to train an LSTM like this with a slightly different objective and get much better sentence representation. And I strongly recommend that you look at it if you have the chance. It's called the Skip Thoughts Vector. So another very nice thing that can be done is to combine modalities. So with deep neural networks, you don't care what input you get and you don't care what output to produce. So one thing you can easily do is to take a convolutional neural network. You can take the inception model, take the image, you can map it into a vector, and then you produce the answer. Then you produce a sentence which tells you the description of the sentence. And you basically just have a convolutional neural network and it's just like the translation work, but we replace the LSTM of the input with a convolutional neural net. And the results are very cool. You get something like two pizzas sitting on the top of a stove-top oven, a man holding a tennis racket on a tennis court, a group of young people playing a game of frisbee. The results over the past, the results have become quite good, and the data set that was used for this work has only 80,000 images. That's MS-COCO. So think of how well the system would do if it had 10 million images instead of 80,000 images. So you can clearly see that these models, the fact that image captioning is possible so directly, I mean, I think it's remarkable. This was done by Oriol Vinyals, Alexander Toshev, Sami Benji, and Dumitru Erhan. And in fact, when they were doing this work, I was so sure it wasn't going to succeed. I tried to discourage them from doing that, but luckily they persisted and they were able to get these great results. In particular, one other very nice application that can be done is that you can train these models to do reinforcement learning, and that's been very successful as well. This is work done by our colleagues in DeepMind, where they directly learn to map pixels to actions with similar kind of models, but with a different training objective. Now, there is one last thing I would like to discuss in the presentation, which I think it's a very interesting, very important new development in deep learning, which, in my opinion, is changing everything. It's very recent, but you should be aware of it. And this development is called attention models. So I apologize in advance. My slides on attention model are slightly rough, but the meaning you should still be able to understand the meaning. So there are two general approaches to attention. What does attention mean, first of all? Attention means that we want to set up a model that can, in effect, learn to decide which part of the input it wants. And so there are two general approaches for attention model. The first one is to use a smooth differentiable approximation to the attention function, and because it is differentiable, it can be trained with backpropagation. And it was first done by Alex Graves in 2013, and later was done by Dima Bogdanov and others from Montreal in 2014. And that was the Bogdanov paper is the way that soft attention is the standard way in which soft attention is done right now. And there is also the notion of hard attention, where you make a hard decision as to where to look, which you then train with reinforcement learning. And it was done by Vlad Ni in 2014 as well. So I will focus on soft attention because it works really well. It's really easy to implement, it's easy to use, although it's somewhat computationally expensive. So let me explain to you why is it so good. Because it achieves the best results in machine translation, syntactic parsing, speech recognition, although not in vision. So in speech recognition, so let me elaborate. So right now there have been multiple papers that show, for example, state-of-the-art results on English to French and English to German, which using attention models that are much smaller than the LSTM model that I was using for translation. But then the same model also achieves great results on syntactic parsing. In fact, an attention model achieved the best results ever on the syntactic parsing task. And what's really shocking about the parsing result is that, I don't know if many of you know that, but parsing datasets are small, really small. There is one parsing dataset that is pretty small. And if you train an attention model on the small dataset, then the results that it will achieve will be almost as good as the Berkeley parser, which is a dedicated parsing system. And that's really remarkable. It means that the attention model is data efficient. It means that it doesn't need as much data as perhaps neural networks of all times needed. Speech recognition is another great one. The colleagues on my team, they have written a paper where they show that using an attention model, you can get results which are almost as good as a really, really strong system on a very large scale data set. So you got a model which is really, so I mean, I don't know if many of you know that, but speech recognition systems are extremely complex. And this attention model is much simpler. Now, how simple an attention model is? Well, you can implement one yourself in 30 lines of piano. It's that simple. So let's discuss how attention works. Unfortunately, I don't have a great figure for attention, but I will try to do my best with this one. So the way attention works by introducing time. In other words, instead of traditional neural networks would process their inputs in a parallel operation. But attention models introduce time. They process their input with an LSTM. So the big square here is an LSTM, and the LSTM, what it does, at each time step, it computes a vector. Now this vector, we compare this vector to every location, or every word, or every position in the input. We do the comparison with a small neural net, which I'm not showing here. There is a small neural net which compares the query vector with the appropriate input. And the small neural net produces a scalar which tells us the quality of the match. We then take the scalar, so you have a distribution. So as a result, you have a bunch of scores. You have a lot of scores for the inputs. You take these scores, you apply them you give them to the softmax function, which turns them into a probability distribution, and then you take a weighted average with this distribution over the inputs, and that gives you the next input. And this process is basically so what's happening here? First of all, everything is differentiable. You only use multiplication and the softmax function. And that's it. So you can implement soft attention if your system supports multiplication and the softmax function. And the second is that you can clearly see that if your softmax distribution is concentrated in one part of the input, then the weighted average is going to be concentrated there as well. And or it could be at a different part of the input. So by using distributions over inputs, the model can behave as though it is focusing on different parts of the input. And this just works. Attention models work really well. I think they are this is, in some sense, I think it is a qualitatively new development in machine learning, and it just makes it possible to solve. You can have any input you want of any complexity. You could have a graph, you could have whatever, and the model will do very reasonable things. You will be able to get results which will be very hard to beat by other means. And so I think with this, I'm already at the end of my talk. It came out slightly shorter than the full hour, but deep neural networks are really, really effective. You can train them. They're easy to parallelize. They can achieve very good performance, and on lots of different tasks, on vision, speech, and with attention, you can now solve an even greater variety of tasks in language and pretty much whatever you want. And with this, I want to say thank you very much for your attention, and a lot of this work was done by many of my excellent colleagues at Google Brain. Thank you very much.
Илья, большое спасибо. Есть какие-нибудь вопросы? Ну, хорошо. Илья, меня слышно?
Слышно.
Алло.
Да.
Да, ну, судя по всему, вопросов нету, поэтому давайте еще раз поблагодарим Илью. И хочу... Да, вопрос?
Внимание и память. Вот, про внимание было сказано, вот про память. Слышно меня?
Да, слышно.
Отлично.
Ну, ЛСТ.
Да. Память это тоже очень важная идея. Я ее забыл упомянуть. Но с памятью есть небольшая проблема. На сегодняшний день память не достигла полезных результатов, а внимание достигла. Память это еще больше, она еще себя должна показать. В будущем она непременно себя покажет, но внимание уже себя показало.
А можно ли сказать примеры, где внимание хорошо себя показало, потому что все время говорится, что оно вот-вот внимание достигнет state of the art.
Оно достигло.
Где оно превышает?
Оно превышает в переводе и в парсинге. Syntactic parsing. В распознавании речи она еще не превышает.
Еще вопрос?
Да. Насчет мультимодальных, вот вы, можно чуть подробнее, какой там state of the art сейчас?
Ну, как бы,
Текст с табличками, с графиками.
типа image to text, да, это вас интересует?
Нет, не one-shot, текст плюс графики, плюс картинки. Вот,
Ну, вот как бы, смотрите, мне немножко, как бы, я знаю, что state of the art в image to text это тот подход, что я показал. Нейронная сеть считывает, превращает изображение в вектор, а потом LSTM выводит слово за словом из вектора. Он не использует, интересно то, что state of the art в image to text не использует внимание, хоть и люди, и другие ресерчеры пытались использовать внимание. Там просто как бы много деталей, что надо было некие детали сделать, чтобы все хорошо работало. И как бы я не знаю, как описать, как бы трудно объяснить как бы с табличкой. Табличка скажет, хорошо, там blue score 32. Ну что это значит? Ну как бы вот если смотреть на примеры, как она выдает из description, описание on the test set, там более легче почувствовать, насколько она хорошо работает.
Я, наверное, другое спрашивал. Я спрашивал про multimodal. Текст, научный текст с графиками, с таблицами.
Ну как бы я не знаю про сильную работу в этой области, потому что нет хорошего датасета. Как бы если построить датасет хороший, то непременно сработает, у меня нет сомнений. Но просто сейчас нет хорошего, как бы нужен датасет.
Понятно.
Ну, например, знаете, что можно сделать, я думаю, довольно без особой сложности? Например, сделать систему, которая возьмет изображение текста и превратит его в латекс.
Ну, это уже Карпаты делал. Он же латекс генерирует.
Не. Он как бы, то, что он делал, просто выдавал латекс, рандомный латекс. А что я говорю, если я возьму фотоаппарат, сфотографирую мою страничку и превращу эту страничку в латекс?
Ну да.
Вот это можно сделать. Я думаю, это было бы очень интересно. И с табличками, и все. Это знаете, как можно скачать там миллион статей с архива, рендерить их, и потом научить нейронную сеть превращать изображения в латекс. Это, думаю, очень интересно.
Файнридеру есть для этого, это да. Нет, понятно. Но там в латексе с фотографиями не очень, поэтому...
Ну хорошо тогда.
Да, и, коллеги, кстати, обращаю ваше внимание на то, что относительно недавно стало известно, что Илья вошел в топ-5, в топ-35 инновационных инноваторов до 35 лет по версии MIT Review. Поэтому предлагаю поздравить Илью и еще раз поблагодарить с этим.
Ну отлично. Ну давай, до свидания, всего хорошего.
Да, спасибо, Илья. Пока.
Пока.